Thanks everyone for attending today. We're really looking forward to this presentation and being able to talk to such a diverse group of engineers. So welcome to today's Measurement Devices Introduction Tech Talk, which is presented by Swagelok Central Ontario and Atlantic Canada. We are one of more than 200 authorized Swagelok sales and service centers located around the world in 70 different countries. I'm Tim Phillips, Marketing Manager, and leading today's Tech Talk is our Training and Technical Support Manager, Phil Reid. Before we get started, a few housekeeping items. Please use the Q&A feature for all questions. Questions will be answered periodically throughout the session. If you have further questions after the completion of today's Tech Talk, please direct them to Phil Reid, whose email you see on the screen, or the technical support team at your local Swagelok Sales and Service Center. We understand through extensive global research and firsthand experience that businesses are under pressure to do more with less, to maximize system performance while juggling smaller budgets, skilled labor gaps, and changing safety requirements. The COVID-19 pandemic only adds to these pressures. Swagelok and its sales and service centers, like Swagelok Central Ontario, Atlantic Canada, are here to lend a helping hand, to provide you with the right resources at the right time. Swagelok Central Ontario and Atlantic Canada has 3 locations: Mississauga, Ontario, Ottawa, Ontario, and St. John, New Brunswick. And we provide local engineering and technical support across Central, Eastern, and Northern Ontario, as well as all of Atlantic Canada. We are one part of an extensive global network of Swagelok sales and service centers that are here to help you with your applications and share knowledge through extensive training and our system evaluation offering, much of which we are adapting to provide virtually to you. Whether you need help with an application or to improve your knowledge in a specific area, whatever your pressure, think of us as your solutions provider. Now I'd like to pass it over to our Training and Technical Support Manager, Phil Reid, to lead the Measurement Devices Tech Talk. Phil, take it away.
Thank you, Tim, and welcome everybody. Good morning. Hope everybody's well. I'm Phil Reid, Training and Technical Support Manager for Swagelok Central Ontario and Atlantic Canada. My background has been in mechanical fluid system design, piping design. I've been with Swagelok now over 33 years, and I manage a team of field engineering, training specialists, fabrication, assembly services, and engineering resources. And joining me today for technical support is Andrew Wright. Andrew is a professional engineer. He's our Senior Engineering Manager for Central Ontario and Atlantic Canada. He is a graduate of Dalhousie and attended St. FX. And Andrew's areas of expertise are in grab sample systems, large refinery systems, analyzer, instrumentation and sample specialties, hose advisory systems, high pressure systems, pressure regulators, custom fabrications, and project management. So Andrew has a pretty full plate, and he's available to reach out to at any time you have any questions, and we'll be providing Andrew's contact information later in the session. So with that, let's get started. Today we're going to have a talk around very high level around fluid system measurement devices. And the devices we'll talk about today are the most common devices found in fluid systems for measurement. And those devices are pressure gauges, transducers, flow meters, and thermometers. So we're going to take a fairly high-level look at these items. Pressure gauges, today we're going to talk about operating principles. We're going to talk about Boredom Tube, which is the most common type of pressure gauge. There are others out there, of course, and we'll touch on those. We'll take a high-level look at transmitters and how they work. And specifically, when it comes to flow meters, we'll look at variable area flow meters, and we'll explain why we talk about the devices we're talking about today. And then when it comes to thermometers, we'll be talking about bimetal thermometers. And these are the most commonly found in fluid systems. And again, the Boredom Tube type pressure gauge accounts for well over 90% of the pressure gauge market. So let's take a closer look, and we'll start with pressure gauges. Pressure gauges conform to ASME B40.100, and what B40.100 is it's a consolidation of a number of standards that used to be out there. And so specifically today we're going to talk about B40.1, which is pressure indicating dial type elastic element gauges. We'll touch on diaphragms, little snubbers, and we'll touch on some of these. But what this standard is about B40.100 is it gives you the direction, it's the terminology, the definitions, safety and construction of gauges, how the markings are on the dial or the face of the gauge, the type of lens, general recommendations, and again, manufacturing. So with that, Swagelok standard pressure gauges are designed and built to ASME B40.100, and they're locally stocked and readily available for you. We have technical people available to answer questions. So let's take a look. What is a pressure gauge? Simply put, a pressure gauge it mechanically senses fluid pressure and converts that into a mechanical motion. And what we're going to talk about today during this session is how that happens. So here we have a cutaway of a pressure gauge, and if you were to look into ASME B40.100, you'd see a very similar picture to a couple we're going to refer to here. So we've got pressure coming into the pressure connection, which can be pipe threads, can be a tube adapter, can be many different ways, any type of pressure connection. And as pressure enters, it flows through to the socket. It goes into the Boredom tube, and the Boredom tube is a C-shaped tube, and we'll talk a little bit further about this as we move along. On the end of the Boredom tube is a end piece, which has a mechanical link or pull rod in here, and this goes to the movement, and the movement is pinion gears, springs, segment gears, and these movements are actually made in Switzerland. For us that are been around long enough when mechanical watches were still very popular, like a Rolex, the mechanical movements are made in Switzerland actually for these gauges. So they're sensitive. You don't like to drop pressure gauges. It can throw off the accuracy. It can do a number of things. Actually jump gears, and the springs can be damaged as well. Moving out to the outside of the gauge, we have the face or the dial, and we have the movement, the face, and the dial. And then last we have the pointer, which is what indicates on the face of the gauge what pressure you are reading. So we'll take a little closer look. Again, ASME B40.100 lays out the case, which contains all of the components. The pressure assembly, this will be the Boredom tube and the socket and the pressure connection to your media. Inside you have the mechanical movement that I talked about. You have a dial or face, the pointer, which will indicate the pressure. You will have the window or lens, and then you have a retaining ring, and these can be screwed, bayonet mount, they can be crimped. There's many different ways, and again laid out in B40.100 how these are designed and built. So let's go a little bit further. Inside a pressure gauge, and specifically a Boredom tube pressure gauge, has a C-shaped tube, and what this is, just a round tube that's been flattened, and these tubes are used in pressure gauges from 10 to 1,000 psig. And again, that would be based on the wall thickness, and these are various materials. They can be stainless steel primarily in all of our pressure gauges. Copper shows up nicer on the slide, so we have copper here. They can be Monel or other exotic alloys depending on your application. So we use the C shape in the 10 to 1,000 psig. Now, how does a Boredom tube work? If you've ever been to a birthday party, and I'm giving Andrew's daughter a shout out today, it's her birthday, and so you may have a party horn. If you apply pressure, we think of We think of this end as the pressure connection going to your media, your system media. And as you apply pressure through the socket to the Bourdon tube, it wants to straighten out. And that is then turned into a mechanical motion to give you a readout on the dial or the face of the gauge. And once you've applied pressure, it straightens out. And when you reduce the pressure, it starts to come back. So that's how the Bourdon tube actually works inside the pressure gauge. Let's take a closer look now at what that really looks like. Going from the party horn back to the inside of a pressure gauge, and a few things that I will point out here. This has a tube adapter connection, so you can face this gauge any direction you want and tighten it, as opposed to an NPT thread where you're trying to get it positioned and get the thread in the right engagement. Pressure enters. Here's the Bourdon, the tube stub I was talking about. Pressure enters through the pressure socket, through into the Bourdon tube, and as pressure is applied, it tries to straighten this out. Pulls on the linkage into the mechanical movement, which transfers that fluid pressure into a mechanical motion as we go around to the front. If it's a positive pressure, it will indicate in a positive pressure. Now the markings, as we talk about, are laid out in ASME B 40.100 based on the range of the pressure gauge. A few things I'm going to point out about this gauge. This gauge is a compound gauge, and it's a dual scale gauge. This gauge reads in positive pressure, it reads in kPa and PSI. And in negative pressure, this will read in inches of mercury or negative kPa. So a compound gauge, so if pressure is applied, it would try to straighten the tube out. If it goes into a negative pressure situation, a vacuum, it will draw the tube down, and that will be transferred to the dial, and you'll read a vacuum or a negative pressure on the outside. Just a couple other things I'll point out on here. It'll always tell you what the materials are. What the wetted materials are. In this case, coming from the pressure connection through the socket to the Bourdon tube is all 316 stainless, and you may be able to see that on your slide. So it's 316 stainless and tube and connection. There's other information laid out on here. This happens to be a 4.5 inch, what's typically called a process gauge. And just one other thing that I'll point out, these gauges have a solid front. So if there is a failure in the system, a catastrophic failure, where the Bourdon tube has been compromised or something else, the media, it's designed so that the back will pop off. It's not going to come out, it's not going to come out through the front where the operator or someone may be there looking at the gauge. So these safety features are built in. This has a solid front. It's a thermoplastic case, used a lot chemical plants, power plants, and pulp and paper. Most industries will use these type of gauges. Moving on a little bit, if we have pressures over 1,000 psig in a Bourdon tube type gauge, we will use a coiled Bourdon tube. And again, it's stiffer. This one you can see is at 100 bar. So, about 15 psi per bar. So getting into fairly high pressures, you get up in that high pressure range, you will have a coiled Bourdon tube. And of course, the tubing wall thickness will be much thicker. Having said that, let's take a look inside a wound Bourdon tube. Looks very similar inside. We have the pressure connection going to the socket, where we have the Bourdon tube welded to the socket, and then it's coiled in the back. It goes to the link, goes to the linkage, the end piece to the linkage, to the mechanical movement, moving back around to the front. Here we have a dual scale gauge, and we can see this is going to 3,000 psi, so therefore we have the helical wound Bourdon tube. And this is no longer a compound gauge. This is a dual scale gauge, but this will only read positive pressure. Once again, just noting that the markings on the face of the gauge are laid out, so regardless of the manufacturer, if they're manufacturing to ASME B 40.100, those markings will be indicated in exactly the same way. This gauge as well, it has the lens ring that we talked about earlier in the presentation. This can be removed. The lens can be taken out, and this is a calibratable gauge. So this gauge can be calibrated. Most gauges tend to be calibrated on an annual basis. We have some customers that calibrate every 3 months, and we have others that leave them up to 3 years. So that is dictated by either your ISO or your QA. So these are calibratable and adjustable movements. So now let's move on, take just a quick look at maybe some of the types of gauges that we have. And some of the types of gauges will be the process gauge that we talked about. It will be typically that thermoplastic case, solid front, blowout back. These can be liquid filled as well, and we'll talk a little bit about that. Then we get into what are known as industrial gauges. Industrial gauges tend to be a stainless steel case. They can be a solid front as well, and that would be called a safety gauge, similar to the process gauge. So it would have a welded in solid front with a compromised back. When I say that, what that means is that it's like a diffusible plug or something that will blow out. And if you have a catastrophic failure, it will blow out the back of that gauge. And these can go up to 6 inches in face, and a lot of the same features. These can have a crimped front, a bayonet mount front, so that you can get in to do calibrations on a lot of these gauges. If it has a crimped front, on the gauge, I apologize, I was pointing at this and I lost my pointer. But so the safety gauge blows out the back. The industrial gauges, being stainless steel, will again have different types of fronts. So that, as I mentioned, the bayonets are a screwed front. We look over here, we have an industrial pressure gauge with a diaphragm seal, or otherwise known as a chem seal. And what this does is this separates the media from a fill media that would be put into the Boredom tube, very specific amount, and this will have a chemical barrier, and that's a diaphragm. It can be exotic alloys, it can be Monel, there's various things, titanium, barriers in there, or it can be plastics, it can be a polymer, it can be PCTFE or something else. And these again can be used for cooling, chemical isolation, so that if you have a corrosive media that you don't want up in here, or you have media that can cause plugging or has a nature that might be very viscous and you don't want it setting up inside the gauge. As you can see along the bottom here, we've put a few others on here just to give you some of the magnitude of gauges, and this is probably less than half of what there are. Down here we have a diaphragm seal on the bottom. This is used in sanitary applications, food processing plants, excuse me, food processing plants or those types of things. Again, a diaphragm. Here we have an electrical connection. You may want to have set points on here for a max or min that would send a 4 to 20 milliamp signal back to a panel. Differential pressure gauges as well, vacuum gauges. So many different gauges and types of cases, and panel builder gauges, and you know, plastic cases, brass cases, various other materials are available as well. So having said that, a couple of the most common gauges that we get into for specialty applications will be oxygen. And an oxygen cleaned gauge will have the symbols on the front of it, no oil. It will state oxygen. Here we see the material of construction on the wetted components. There's a bit of other information on the front here that we won't get into today. But this gauge is a compound gauge, again, reading positive pressure up to 400 psi or up to approximately 30 bar. And again, this is a removable front with a, pardon me, this does not. This has a crimp front, so therefore you can't get in to calibrate this gauge. You can see how the front is crimped onto this gauge, and it uses a polymeric lens versus a glass lens. So if this gauge is cleaned to oxygen cleaning, and anything over about 23.5%, you should be using oxygen cleaned components. So this gauge is manufactured and packaged in accordance with ASME B40.100 cleanliness level 4, suitable for oxygen service, and the dial markings are as per ASME B40.100 as we discussed. Something else I'm just going to point out on this slide. We can see this little valve here. The little valve is used, if this gauge were shipped, and I've had it set here, you can see it's not it's not right down to zero. So this will relieve pressure from inside the case. So if this gauge has been on an airplane, flown across the country, and it builds up pressure inside the case, you can get a reading on the dial when you receive the gauge. By simply cycling this little lever back and forth, you will allow that to vent excess pressure in the case and then seal it up again. And that also, that little plug is where we fill if we're putting a media inside there, glycerin filled or water glycerin filled gauges as well. Another very common gauge, again very specific to industries, is a pneumonia gauge. And people say to me, well, Phil, look at this gauge. It's got you're combining temperature and pressure. So like steam, steam at a specific PSI has a correlating temperature. So if we're looking at 250 pound steam, we're looking at somewhere in the neighborhood of 400 degrees Fahrenheit, or so about 400 degrees Fahrenheit. And ammonia has the same. So as you pressurize ammonia in large refrigerant systems, it correlates to a specific temperature. And you can see here we have it marked in Fahrenheit and PSI here, and inches of mercury in a negative pressure situation. So this gauge, if you were to take ammonia and put it into that situation, these would read out the correlating temperature of that specific gauge. Also, you note again the little flip lever on the top to equalize pressure inside the case. One other item I'll mention, this is a crimped front on this gauge. This front cannot be taken off to calibrate this gauge. So this gauge would not be able to be taken apart or get in to be able to calibrate. Having a look again, we talk a little bit about the specific gauges. We talked about compound process gauges, stainless steel gauges down to about 1.5 inches on the face. And depending on the application or how you might want to choose it, you might want a center back mount, a lower tube adapter. There's many different types of mounting options as well. And next slide. So gauges have an accuracy range. So if the range, and they're laid out in what are known as the lower, got my pointer again, the lower third, the middle third, and the upper third. Pressure gauges are typically most accurate in the middle third of the gauge. So this would be where they're most accurate. The gauges we provide have the same class all the way across the gauge, all three equal areas. So if you have plus or minus 0.1% of span, what that refers to, they take 5 separate readings on this gauge. And the percentage of span, it has to maintain accuracy to within 0.1% of span. If you were in a D class gauge, it would be plus or minus 5% of span. So being arbitrary here, if we had a 0 to 100 PSI gauge, we may be at 105 or 95 if we're using a accuracy grade D. We have, most of our gauges are a 1A class, and they would have a plus or minus typically 1% of span or better. So a little bit about diaphragm seals, and we're going to take a break for some questions here in just a minute. A little bit about diaphragm seals. So a diaphragm seal, as I talked about a little bit earlier, it has the process connection on the bottom. It has a diaphragm separating the fill media, and this is a very specific amount of media that's put in and then welded closed. The capillary extension, these can be extended out in various lengths, and they can be used for cooling, or if you need to put the gauge in a remote area from where you're actually taking the measurement. So these can be done in various types of gauges at various lengths. Then the system fill media, as I talked about, is inside. The various components that we talked about earlier in the presentation are contained in the gauge. So where would you use this? If you have a lot of pressure spikes in your system, This will reduce the effects of the pressure spikes on the gauge. You can also liquid fill the gauge itself to dampen the movement and help provide lubricity and other things. So where you have pulsation, where it's pulsing back and forth, this can help dampen the effects on all those little gears that I talked about in that movement inside. The mechanical movement is a delicate movement, and it's very accurate, just like a Swiss watch, and can be damaged from pressure spikes, pulsation, and things such as high temperature. We can isolate the gauge and put it remote from where the temperature is. Corrosive media, we want to keep corrosive media out of the internals of the gauge. We use a chem seal or a diaphragm seal. There could be suspended solids, highly viscous or crystallizing or clogging media. This orifice going into the gauge is about 0.6 millimeters, so it's very small going into the gauge. And again, it acts as a chemical barrier or a thermal barrier. So lots of applications, and we'll just have a closer look here at an actual one. We had this picture up a little bit earlier, but this is what the seal would look like. This is a very short capillary. This could be lengthened out. Just back to this gauge for a minute. This happens to be a compound gauge, single scale, reading in bar only, and all the internals of this gauge are 316L for this application. So this is a positive pressure, negative pressure gauge, and that would be a compound gauge, but not dual scale. Okay, so just a few things here before we move on. Some of the most common gauge failures: pressure spikes. And we get gauges sent back to our factory and people say, no, it's impossible that it could be. We can tell as soon as we take the back off that gauge if it's experienced a pressure spike. There are many indicators. And the same with overpressure, very common. Mechanical vibration, where the gauge is moving around, that has an adverse effect on the internals of that gauge. Pulsation, back and forth, again, you can imagine what that's doing to the gauge. Temperature can affect the gauge. Corrosion, clogging media, and mishandling and improper use as well can be an issue. So with that, a few things before we take some questions. It is important to note when you're going to select a gauge, you want to know the composition of the fluid you're measuring, the temperature. What are the ambient conditions? Is it in a corrosive environment? Is it in a hazardous environment, a dark area? You may want to get a reflective lens in the back of this, which is available as well. You want to know the pressure range, and remembering that you're most accurate in the center third of that gauge. So if we were trying to measure 100 psi-G, I would select a gauge 0 to 160, typically. So again, the conditions affecting the wear of the system. So is there a lot of vibration? Is there shock? Is there impulse? Those types of things happening. The method of monitoring this gauge. How are we going to be checking on this gauge? Is it in a location that's going to be accessible to read the face? And then you want to know the required accuracy of the system that you're working in, and as we said, the grades of the accuracy we have listed. And with that, we're going to take a break, and Andrew, there appears to be a few questions. You may want to answer a couple of those, and for the sake of time, we can move on. We'll be happy to stay on after as well. Andrew?
Hopefully everybody can hear me okay. First question, this is from Marcel Boudreau. Do the higher pressure gauges use helical tubes because the highest pressure application requires stronger and therefore stiffer materials? So there's a couple ways to look at this. So Phil talked earlier about the calibration and the sensitivity of the Boredom tube and working within a specific range. So the C-type Boredom tubes have generally are on the lower pressure ranges. With the helical types, you have much better sensitivity at the higher pressures, and they're a bit more robust. So it is a more robust solution for those higher pressures. So overall, that you will see those helical tubes in the higher pressure gauges. Anything you want to add to that, Phil?
No, that's good, Andrew.
Okay. Second question. This is from Michael Dentino, who would typically calibrate a gauge? Is that something Swagelok would do, or is this something a tradesperson could do? So when you buy fresh gauges from brand new out of the box, you can buy them with calibration or without calibration, and that's something that Swagelok can offer should it be required. So when you go through the catalogs, there are options to include pressure gauges, and with those pressure gauges you can get a calibration certificate. Once those certificates generally last about 1 year. And then after, generally for pressure gauges, you would want to get them recalibrated every year should calibration be required. So you could either send them back to Swagelok and we can send them back to our factory for recalibration. There are other service providers out there. Now I looked up in the Dartmouth region, there's one called Pylon. We also have Pylon in Ottawa. And they're third party. They have the codes to calibrate or recalibrate a gauge that's already been used. So highly recommended. We've used Pylon in the past and other companies such as that to recalibrate gauges. So great question. Michael, yeah, sorry, go ahead.
Typically you want to have calibration traceable back to NIST or NRC. And so a company like Pylon that Andrew mentioned, that you can go right to ISO 17025 and higher levels of calibration depending on your application. So we deal a lot in the nuclear industry. 17025 is a requirement. Thank you, Andrew.
No problem. And B40.100, there's some calibration standard requirements that are out there that people can do a little bit of research on as well. All right, next question. If you can't calibrate the gauge, would you have to replace them after a specific time? Is there a standard age depending on the type? And this is from Martha. So often, Martha, it comes down to code requirements or the application that it's put into or specifications around the project. I've seen commonly that gauges should be recalibrated on an annual basis. But I've also seen applications where calibration isn't required at all. So it comes down to the application that you're working on and to do a little bit more digging into that, and you should be able to find some answers. But general rule of thumb, if calibration is required, they should be recalibrated on an annual basis. So the next question is from Jason Ledbetter. Does ASME 40.1 oxygen cleaning clause refer to compliance and adherence to ASTM G93? So it does. There are linkages between the 40.1 and G93C. So having the B40.1 does clean the gauges to be able to use in an oxygen system. Phil, you might want to jump in here. If B40.1 actually references G93, I don't know offhand, and I might have to do a little bit of research and get back to you on this one.
No, that's fine. So no, it doesn't, but it's a cleaning, it's the same thing. ASME just kind of moved it over to B40.100. There are connections between the two, as Andrew mentioned, but it doesn't reference direct correlation. If you need it to ASTM G93, C or B levels or whatever, you'd have to indicate that to us when you are buying a gauge. We are in the midst, you may be with the military, but we're in the midst of working with the military currently to have it changed to the ASME B40.1 specification versus the G93C level. So they are virtually identical to G93C for the B40.100. If you want more on that, I'm sure Andrew will be happy to, you can reach out to us and we'll be happy to continue. Okay, with that, I'm going to move on. We're a little bit behind, so hopefully I apologize for that. But great questions, and that's what really makes these things work. So we're going to move on. We're going to talk at a very high level again. We're going to talk about some transducers, many different types of transducers out there, and really, different types of connections, flying leads, various types of electrical connections here as well. And with that, what is a pressure transducer? Well, a pressure transducer is an electronic instrument that senses pressure. There's a diaphragm in the transducer that is pushed against. And what it does, it converts that applied pressure into an electrical signal, typically a 4 to 20 milliamp signal being sent out, to either a point of use indicator or back to a panel or to something else. So the signals can be put through a PLC, they can be recorded, or they can be used to change system parameters. If you want, you know, if you're making grape soda and you want more water or higher pressure to run something, you know, it might change something in the system for you. So typically used for monitoring and can be sent back from a remote location. Excuse me. And so the big thing about it is that a transducer can be used where you need remote sensing in a system, you know, you need a higher level of accuracy that we'll talk about, or it may be in an area that is hazardous and you know, you're not going to be able to get in there to read a pressure gauge and you want to be having these readings sent back to a control panel or back to a control room. So again, many different applications, explosion proof, etc., intrinsically safe, and with that. So how does a transducer work? Well, it's a thin metal film piezoresistive sensing technology. And what the heck does that mean? So like a semiconductor, it's an etching on a wafer, and we'll come back and talk a little bit more about that. But it's all stainless steel construction of the whole unit, so everything is stainless. We have temperature and accuracy compensated. You know, it has a circuit built in to compensate for temperature. The standard or explosion-proof models are available, so depending on the application, where they're going to be used. And again, performance advantages with a transducer, you know, you get stable, repeatable accuracy, very stable over the long run. They're not as susceptible to mechanical damage, and there's a lot of design flexibility. But keep in mind, you will need power at this. It sends a 4 to 20 milliamp output signal. So again, typically instrument signals that you'll have in plants or where you're working. And so these signals will go out, and you know, they're very stable and repeatable, as I mentioned. So let's take a little look at what we just talked about here. So the diaphragm here is like a strain gauge. It's strain sensitive. It's a Wheatstone bridge, which typically it was just Dr. Wheatstone that invented that back in the 1800s. And really what you're doing is you're comparing, in the shortest answer I can give you is you're comparing a known to an unknown. And like a strain gauge, as we apply pressure to this thin film and it changes the resistance of the circuit, of that printed circuit. It's like this is like a semiconductor wafer, and it compares the two and transforms that into, or converts that into, an electronic signal that is sent back. So it's made of a very stable thin film. It's deposited here in a atomic layer deposition, and so, you know, it's like a microcircuit etched into a wafer. Once you apply pressure to it and it starts to strain, it changes the resistance and transfers that again into an electronic signal that would be sent back to your control panel. So the thin film piezoresistive sensing technology, some of the great things about that is it's very stable. So long-term stability is less than or equal to 0.2% of span. And if you remember when we looked at the, when we look back at the percentages of span on dial-type Boredom Tube pressure gauges, some of them were up to 5% plus or minus of span. So where we use this is where you have a very stable, long-term, excellent repeatability. Again, less than or equal to 0.1% of span. You know, accuracy levels are at 0.5% of the span or equal to, and then minimum temperature errors. These are compensated for as well, as I mentioned, in that temperature compensating circuit. And one thing that pressure gauges don't like much is a lot of shock and impulse. So the diaphragms are much more resistant to that shock and impulse in a gauge. So a few models, just to give a general overview, and again, really many manufacturers out there. But there's the general industry models, which would be in things like process control test equipment, or on hydraulics and pneumatic systems where you have remote sensing required. And then if you get into more specifically designed or applications to meet the durability and performance required, where there's explosion-proof systems required, such as wellhead monitoring and petrochemical applications. Offshore oil and gas use a lot of intrinsically safe or explosion-proof models, and these have factory mutual ratings. You can see CSA, CE for European countries, and various parts of the world. So we're a global organization, so we have to adhere and conform to many different standards throughout the world. Arrow here to move. So typically we just look for a little bit of information. If you're going to be looking to buy a transducer and you want to know, again, you're going to want to know what that pressure range is going to be. You're going to want to know what units of measurement you're going to be working in. What output signal is required? Quite often, typically the 4 to 20 milliamp output signal. Is there a power supply available for instrumentation? Electrical connection required. There's gosh, I believe there's like 17 different electrical connections available for these units, and there's about 9 process connections. So BSP, ISO, tube adapters, fractional and metric, face seals. So there's a number available. And how it's going to be connected to the pressure source, as I just mentioned, several connections, and any special requirements. Do you need calibration certificates, material traceability certificates, certificates of conformance? Any of those types of things are definitely available, but at the time of placing an order, if you need a material traceability certificate for the materials, it has to be at the time of order. And with that, Andrew, do we have any questions from our group today?
We're limited to pressure transducers, but Rosemount, for example, it offers quite a variety of temperature and humidity-based transducers in the market. So highly recommend. They're great products. We've used them in many of our solutions in the past, but again, Swagelok, we're limited to pressure transducers.
And WICA offer a very good range in those areas as well. Okay, thank you. We'll move on, and again, as I said, we're not going to jump off here. We'll stay for questions. Next thing we're going to look at are variable area flow meters. And when we talk about flow meters, some of you may be familiar with Coriolis meters and various other types of meters, and they can become very, very expensive. So the devices that we're talking about today have typically low setup costs, highly accurate, meet codes and standards, yet just lower setup costs, easier to use, minimal maintenance, and those type of things are why we selected to talk about these today. So let's have a look at this. And what is a variable area flow meter? Well, a flow meter is a device that operates on the principle of allowing fluid to pass around a float that's in a housing, and we'll take a little closer look at this later. And the tube is tapered inside here, and we'll see a slide in just a couple of minutes that shows this. And as the flow force increases, normally, from higher flow rates, the float will move up the tube, and the tapered tube allows more flow around that annular gap around the outside. So as that ball moves up in the tube, and you get a direct indication at the front, the tube becomes larger. So the measured flow rate then corresponds to a location right on the tube. So let's take a little look at what we're really talking about here. So the advantages of using this type of flow measurement device, very simple. Visual indication of flow. You can see immediately as you're standing there in front of it where that ball is and where it correlates to a specific flow rate. Here you can see the taper of the tube, and as that ball, which has a specific density, and as flow forces increase, it pushes that ball further up the tube, and these have to be mounted vertically, and we'll talk about horizontal mounting in a few minutes. But as this pushes up the tube, the gap, the annular gap around the float becomes larger and allows for greater flow, and therefore correlates to a flow measurement indication. Beautiful thing here, does not require external power. Very low setup costs. You buy it, you install it, it gives you a visual indication. Not a lot of moving parts in here. Less expensive than most flow measurement technologies. It's very simple, very robust, and again, minimal pressure drop across a variable area flow meter. So let's talk a little bit more about how they work. Changing process conditions. So in this flow meter, we see that G equals gravity force, which is dependent, on the mass of the float. Buoyancy, and I guess I better pick a better letter for that, but the buoyancy of the float is dependent on the density of the liquid or gas. And then the flow force caused by the flow rate coming in, and again, this is the fluid viscosity and the annular gap within the flow meter or things. And I might just mention at this point, all our flow meters are calibrated with air or water, specific gravity of 1. I will talk a little bit about why we do that in just a minute, but if there's changing conditions, and most variable area flow meters, or quite a few, will have a metering valve so that you can control flow right at the front of the flow meter, and you can adjust the flow as you're reading it out. Okay, so now what two things could change how this performs? I talked about we calibrate using air and water. So if the density or the viscosity of the media change, it will change our readings if we're set for water. So what changes this? We have density and viscosity. So what changes density and viscosity is quite often temperature and pressure. So these are things that we would need to know. So if you are looking to have a flow meter for another liquid, and other than air or water applications, what we will do is there's some simple questions that one of our technical reps would talk to you about, and that's the fluid being measured, the viscosity of the fluid with units being measured, the specific gravity, temperature with the units of measure and range, fluid pressure with unit of measure, and then again, flow measurement range with unit of measure. So these are questions that we would talk to you about, or if you were working with another manufacturer, they would do the same. Most variable area flow meters are calibrated to air and water. And again, you can reach out to us and we would certainly help you with that. So let's take a little look at these again. We offer sort of two models. We offer these glass tube and some plastic. There's some others, but allows direct viewing, as we mentioned, from the front, and excellent accuracy ranges. The longer the tube, the higher the accuracy. The smaller the flow meter, the lower the accuracy. So again, low setup costs, very inexpensive setup costs here. So as you can imagine, on the glass tube models, there's 6. We also have a plastic model as well if you have very benign or non-aggressive media. So 6 models, they vary in size, accuracy. Of course, as accuracy and size increases, cost will go up, and then the materials of construction may change as well. So those are some of the very specific things. So we have that one model, as I mentioned, that, oops, I'm just going to go back one slide here if I can. So there is one model that is available with a plastic tube. And again, that's just an economy model, maybe you'd call it. I don't know, don't like that word, but we'll use it. So then we have the M. These are metal flow meters. They have a metal tube, and they will use a spring and a magnetic interface. So these can be mounted horizontally, and we'll talk about that in a minute. But the metal tube flow meter is designed for extreme operating conditions, A lot of power plants, a lot of chemical plants, refineries will use this type of flow meter. Also, it can be in a vertical or horizontal model. Here you can see that the metering valve built into the flow meter, and these are known as armored as well because they are metal flow tubes. So often if somebody asks for a armored flow meter, it will often mean that it's a metal flow tube. So as we talked about, the models that can be mounted horizontally, they can have a readout on them, they can be powered up. You can also have electrical connections, those types of things. So the 4 models, they vary in size, accuracy. As accuracy and size increases, so does cost, obviously. What type of end connections? Is it going into a pipe system? Is it welded, threaded, tube fitting, flanged? And then what the orientation of this flow meter will actually be in your system and how it has to be installed. So in these models, very high accuracy at 1.6. These can be set up with limit switches inside, so you can have a high and low, and let's use that 420 milliamp output signal again and have 4 set as our low and 20 as our high. This has a tremendous amount of what we call configurable options. So it's very configurable to the type of system that you're adapting to. Limit switches, as I talked about, are available on the glass tubes, are available in others, and that may be where you want an electrical signal again, letting you know that there's a high or a low in the system, or when you've reached a specific flow rate to stop something or go back to a control valve. So with that, we have a few things that you need to know when you're going to be selecting a flow meter. And a flow meter is a device used, again, to measure the fluid. So you want to know what that fluid is that's being measured. Is it a gas? Is it a liquid? Is the fluid viscosity available? Is the fluid specific gravity? And again, if you're working with water and air, you're fine. You can buy an off-the-shelf flow meter. Otherwise, the calibration will be different. The temperature you'll be operating at, the pressure, the measurement range and the units. What type of connections are you going to have to the source? Are you going to want to have electrical output, that 420 milliamp for a high or a low? And then any special requirements, options, certificates, traceability, certificates of conformance, calibration certificates, many other things that may be required as well. So with that, Andrew, do we have any questions? We can move on to the mechanical temperature measuring devices, and then we'll, like I said, we'll hang out if there's any questions. So the last most common device, again, low setup cost, highly accurate, meets ASME B40.200, etc. And we'll talk a little bit about thermal wells as well in this segment, adjustable faces. So, excuse me, apologies. Here we have a bimetal thermometer, and the wetted components will be all 304 stainless steel, the process connection, the stem tube, the stem tip, and all of these components are welded together to prevent leakage. So you'll have the face, you'll have your process connection going to the system or into the thermal well typically. You will have the 1/4 inch stem, the bimetal helix wire. We'll take a closer look at this just in a few minutes. So it is attached at the end and runs, the staff wire runs up through the stem. And so we'll take a little look at how this works. So a bimetal thermometer works on the effects of expansion, contraction of the two metals. So you have two different metals. The metal with the higher thermal expansion and the metal with the lower thermal expansion. So the bimetal system consists of the two, and they're bonded together. And as temperature changes, the difference in expansion and contraction of the two metals will give a warping effect, and and it causes that. Okay, we need one more click here. Something's not. Okay. Anyway, my apologies. So as it works is you apply heat and it starts this warping effect, and it causes the bonded bimetal strip to bend proportionally to the amount of heat added, and it's anchored at one end, and we'll take a little closer look at this as I mentioned. And so as it starts to expand or contract, it will start to twist on this helical wound bimetal strip in the thermometer, and we'll see where this is in just a second. And the proportional movement of the bimetal strip is measured by the pointer out in the face, and the temperature is indicated on a calibrated dial scale, and we'll take a little closer look at that. And the bimetal system is helically wound and heat treated for long, very stable, long-term life. So here's what it looks like if we were to do a cutaway of cross-section. We've got a bezel which is gasketed and hermetically sealed to the lens, so you don't get fogging inside the lens. I will come back and talk a little bit about anti-parallax and looking at things on the same plane in just a moment. And then the pointer will be in here. You'll have the lens, and there's various lens materials. You'll have the stainless steel case. They are calibratable, so there's a calibration adjustment screw on the back, and it actually doesn't change anything in here. It actually turns the dial on the face once you have either an agitated ice bath or boiling water. You'll have your process connection. You'll have a staff wire inside the stem, and that stem can be up to 72 inches in length or as little as 2 inches in length. So then the bimetal helix is welded to the bottom. And typically you would be threading this stem at the process connection into a thermal well because this is more susceptible to damage than a thermal well, and I'll explain what a thermal well is in just a couple of minutes. Okay, so now I wanted to take a little closer look at that lens area of that gauge. This bimetal case has the bezel. It is sealed so that this lens, it can be instrument glass or there's acrylic lenses as well, so that you don't get it fogged up. There's nothing worse than trying to read a fogged up gauge or thermometer. The maximum ambient conditions for this case are 200 degrees Fahrenheit or 95 C. And again, it's all stainless steel construction. So in accordance with ASME B 40.200, lens and gaskets are hermetically sealed, as we talked about. And this is something that happens in thermometers a lot. They lose a seal. Not these thermometers as much as some of the lower grade thermometers, I guess you would say, that don't use the same technology. I wanted to talk a little bit about the anti-parallax. So what happens is the actual where the scale is printed and where the needle are, they're on the same plane. Where if you had two different planes and you were reading it from an angle, you can get what's called parallax, and you may read up to five degrees off or different, where depending on how you're looking at it, if you don't get a straight look at it. So one of the features on this dial type thermometer, a bimetal thermometer, is that the needle is on exactly the same plane as the scale. Looking a little bit more at how you calibrate, the bimetal thermometer is field adjustable, as you can see. It's got a gear in the back of it that actually turns and it rotates the dial in the face. And that is done through the typical methods that you'd use, either a agitated ice bath or boiling water. You know, and you'd want the calibrated thermometer accuracy traceable back to something like NRC or NIST. So the patented movement, this does not liquid fill, but it has a silicone-free anti-dampener, so you don't get the oscillation on the needle because of this dampened movement, and that would be on the face. Plus, you're not introducing any other media into the system, so it extends the life of the thermometer. Again, accuracy grades, ASME B40.200, grade A accuracy means that across the whole scale of the thermometer, this accuracy will be maintained at plus or minus 1% of scale. So if you were using grade D, for example, plus or minus 5%. But also, thermometers, like pressure gauges, have the most accuracy right at the midpoint. Okay? So ASME B40.200, grade A means that the thermometer has a plus or minus of 1%, and just using a simple bit of math, 0 to 250 degrees Fahrenheit, the accuracy will be plus or minus 2.5 degrees Fahrenheit, or 20 to 120 C, 1.4 C, anywhere along that measuring scale. So it's not just in that middle third. Some options: center back, lower center back, lower back with an angle, or configurable. These are adjustable angle stems. I'll talk briefly about thermal wells. So a thermal well would meet ASME code. It could be a flange, they can be tapered, they can be threaded. But you would put the thermal well into your system, very robust, machined from stainless steel. They would go into the system, and then the stem would sit inside this. So you don't have to, some of the advantages being that you don't have to take the, shut down the system to remove a thermometer if you have an issue with it and it has to be taken out. So thermal wells protect the temperature measuring device from processed media, provide pressure containment. They allow temperature device to be easily removed. And again, if you are putting lagging on or insulating pipes, that type of thing, they provide an extension for that. So many different types of thermal wells. They can be threaded, raised face flanges, socket welds, quick clamp for the sanitary industry. And again, they can be straight or reduced or tapered port. And a few things you need to know when selecting a thermometer. Once again, you're going to need to know the fluid temperature range, the dial size that you're looking for, the units of measure and the scale, the stem length, the connection to the temperature source. Any special requirements, again, we talk about options such as traceability, material traceability, certificates of conformance, accuracy, those types of things. And are you going to use a thermal well as for the process connection? And with that, my friends, do we have any further questions? Okay, thank you, Andrew. Please feel free. We'll provide my email address is on the screen. If there are any questions after the session, or you're looking to speak with one of our representatives, you can send those to me, and I'll certainly make sure they get into the right hands. I also just want to talk briefly about our team of local engineers that are available for you to have conversations with. You've met my good friend Andrew Wright, who is our senior engineering manager here at Central Ontario and Atlantic Canada. We have a team of field engineers and mechanical solutions engineers. Phil was supposed to be joining me today, but somebody at the Halifax shipyard needed him worse than we did, I guess, so he's looking after that. Hassan, who is a solutions engineer. Ali works in our what we call our custom solutions and our fabrication, and he does a lot of mechanical design there. So these are resources. You can reach out. You can, for lack of a better term, pick their brain if you have a question, or myself. Also, we have our Tech Talks and Swage Talks, which are our blogs, and they can be accessed at Swagelok Central Ontario blog or Atlantic Canada. And with that, I will just mention we have other Tech Talks and webinars available. Please reach out if you'd like us to look into one of these, or if you'd be interested in any of them. Mechanical seal support systems and tube versus pipe, and how some of the advantages there. We have hose basics, how to select hoses, regulators, how regulators work. This is a very popular one among our engineering family. And with that, thank you for your time. There is an address here that you can go to if you want to provide feedback, if you felt the session was worthwhile or there's anything that we could do to improve the session, then please let us know, and we'd be happy to work with you. So with that, I'd like to thank all of you for attending, and again, we'll stick around for a couple of minutes if there's any further questions that come up, and I'll leave this up on the screen, and if anybody needs to see the email addresses or anything again, please let us know, or Beth would be happy to let us know if you're having trouble getting in touch with us. Thank you.
Okay, great job, Phil. I just wanted to add with regards to the other Tech Talks, we could set up one-on-one Tech Talks for anybody on the call here today. Just reach out via email, and we'd be happy to set something up for yourself and your colleagues and peers. Thanks.